Here is a combined summary of the 2 pages. The paper addresses the problem of state estimation for nonlinear time-varying systems with uncertain parameters under multiharmonic disturbance. The proposed solution consists of 3 steps. First, an unknown input state observer is synthesized, which, however, requires the measurement of output derivatives equal to the plant's relative degree. To relax this limitation, an alternative representation of the observer is introduced. Next, based on this observer, the unknown parameters and disturbances are reconstructed using an autoregression model and the dynamic regressor extension and mixing (DREM) approach. This approach allows the estimates to be obtained in a finite time. Finally, based on these estimates, an observer is constructed that does not require measurements of the output derivatives. The motivation for this work stems from the challenges in implementing state feedback in automatic control systems due to the lack of measurements of state variables. The installation of sensors can be prohibitively expensive and sometimes technologically unfeasible. To address this issue, control theory has introduced the concept of observers, which provide the estimation of state variables without direct measurement. Classic methods for constructing state observers for nonlinear, time-varying systems under disturbances include piecewise approximation of nonlinearities by linear functions, the extended Kalman filter, and sliding mode-based observer synthesis. However, these approaches have limitations, such as inaccuracies in linearization, the requirement of model linearization and knowledge of perturbation distributions, and the occurrence of sliding modes, which introduce oscillations and high-frequency switching in the control channel. In contrast, the proposed approach does not require measurements of output derivatives, and the DREM approach allows for finite time estimation of unknown parameters and disturbances. The effectiveness and efficiency of this solution are demonstrated through a computer simulation. The paper contributes to the development of state observer synthesis for nonlinear, time-varying plants with uncertain parameters under multiharmonic disturbance, which is crucial for enhancing the effectiveness of automatic control systems. The paper discusses the synthesis of observers for uncertain plants with output-dependent unknown parameters. It highlights the importance of transforming the original system into a linear regression form, which allows the application of various identification techniques such as least squares method, gradient descent, and dynamic regressor extension and mixing method. However, these techniques require fulfilling the persistent excitation condition for the regressor and do not have a universally applicable method for different plant classes. The authors also introduce the concept of unknown input observers, UIOs, which are designed to estimate state vector despite the presence of disturbances and other factors affecting the signals in the control channel. UIOs were first introduced by N. Kobayashi in 1982 and have been further developed for discrete time systems, various nonlinear systems, and time-varying systems. For time-varying systems, a common approach is to transform the original plant into a polytopic form with weight functions that depend on parameters. To construct the observer and ensure its stability, Lyapunov function framework and solution of a system of matrix inequalities are typically used. The paper then presents a novel, comprehensive solution for nonlinear time-varying systems based on the unknown input and the identification-based observer synthesis. This integrated approach aims to address the limitations inherent in each individual method, facilitating efficient operation across a broader spectrum of systems, providing the estimation of the state, with the reconstruction of the parameters and the unknown input in a finite time. The proposed algorithm first assumes the availability of the derivatives of the measured output signal and then relaxes this constraint. It also introduces an algorithm to estimate the unknown parameters and external harmonic disturbances, and state observer based on these estimates that does not require output derivatives. Finally, the paper concludes with simulation results that demonstrate the efficiency of the proposed method. The paper discusses the synthesis of an adaptive observer for a class of nonlinear systems with external disturbances and time-varying parameters. The model under consideration is described by a system of ordinary differential equations with an output signal and a product of unknown variable parameters and an unmeasured state vector. The external disturbance is represented as a sum of sinusoids with unknown amplitudes, frequencies, and phases. The paper assumes that the pair A, C is observable, matrix B has full column rank, and matrix C has full row rank. Additionally, it is assumed that the time-varying parameters vector theta, t, is an output of a linear generator. The goal is to design an adaptive observer that ensures the estimated state vector converges to the actual state vector and estimates the external disturbance and time-varying parameters in a finite time. The observer synthesis algorithm is provided, including the introduction of an exponentially converging state UIO, which describes the basic structure of the estimator. An alternative realization of this observer is derived that reduces the number of needed derivatives to R1 and provides a finite time estimation of the state. The paper also demonstrates that the proposed observer is indeed an observer by showing that the error between the actual and estimated state vectors exponentially converges to zero. This is achieved by solving a system of equations that define the matrices F, L, and G in the observer. The solvability of this system is guaranteed under certain conditions. Overall, the paper presents a novel approach to the synthesis of adaptive observers for nonlinear systems with external disturbances and time-varying parameters. The proposed observer utilizes auxiliary variables to relax the problem of unmeasured output derivatives. By introducing variables z1 to zr, the state vector estimate is given by x equals z1 plus gy, r minus 1, equals zr plus fr minus 1 gray plus gy, r minus 1. If matrix L is chosen to satisfy frg plus L equals 0, then zr, t, equals fzr, t, resulting in an exponentially decaying function in state vector estimate of the form x equals fr minus 1 gray plus gy, r minus 1, plus eftzr, 0. This observer provides estimation of the state vector x, t, with exponential convergence. The convergence speed of x, t, to x, t, depends on the eigenvalues of the matrix F, which can be chosen using a pole placement procedure to satisfy desired transients. Additionally, if L plus frg equals 0, then the state of the system can be immediately reconstructed for all t is greater than or equal to 0. Furthermore, the observer can be used to estimate unknown parameters and disturbances, as well as to further estimate the state vector without using derivatives of the output signal. For instance, by substituting the expression for the estimation of x, t, into the system's equation and applying RTH-order linear filters and the swapping lemma, the terms containing unmeasured derivatives in the regressor for xi, 0, can be eliminated. This approach allows for the estimation of unknown external disturbances and initial conditions. We present a novel approach to estimate initial conditions and disturbance frequencies in a system with an arbitrary relative degree. This method utilizes a series of transformations on the original equation to obtain a linear regression form, enabling the estimation of the initial conditions for the vector xi, 0, and disturbance frequency omega. The original equation is first rewritten as a function of S1, t, which is then further transformed to include a filter and a series of transformations, resulting in equation 15. This equation is then simplified to form equation 16, where the sinusoidal signal properties are applied to obtain equation 17. By multiplying equation 17 by row vector b and applying a second-order filter, we can group the unknown terms to obtain a regression equation 18. This regression equation has the form of linear regression, allowing for the estimation of the initial conditions for the vector xi, 0, and disturbance frequency omega. To estimate these parameters, we propose using the DREM method based on Kreiselmeyer's regressor extension scheme. This method involves introducing the vector phi r, t, and the matrix year, t, as solutions of the differential equations 19. After applying DREM, we obtain equation 20, which allows us to determine each element of the vector kr. This approach provides a systematic way to estimate initial conditions and disturbance frequencies in systems with arbitrary relative degrees, utilizing a combination of signal processing techniques and linear regression. The proposed method is particularly useful for systems where the relative degree is not fixed and can vary during operation. The proposed methodology for estimating initial conditions and external disturbances in mechanical systems is based on the use of the DREM method. This approach allows for the estimation of initial conditions and external disturbances in a finite time, provided that certain conditions are met. The algorithm involves the use of a swapping lemma to solve a problem similar to the case where phi, x, y, t, is a linear function of x, t. In the case of a nonlinear function, the swapping lemma can still be applied, but with modifications to the equations. The algorithm begins with the estimation of the initial conditions xi, 0, and the frequency of the external disturbance omega. This is achieved through the use of a linear regression equation, which can be solved using the DREM method. The amplitude of the disturbance is then determined using Kreiselmeyer's regressor extension scheme. Once the amplitude of the disturbance is known, the external disturbance f, t, can be reconstructed using the harmonic nature of the signal. The proposed algorithm allows for the estimation of the parameter vector even in the case when the regressor depends on the x, t, which is a main difference between this approach and previous solutions. Finally, the state estimation is achieved through the construction of an arbitrary observer of the state vector for the system. This observer does not require derivatives of the output signal and uses the estimates of all unknown parameters obtained in the previous steps. The observation error dynamic model is derived, showing that the error dynamics can be influenced by the choice of the design matrix K. Here is a combined summary of pages 13 and 14. The observer design for finite time estimation of parameters and states in dynamic systems is presented. The Lyapunov function v is introduced, and its derivative is derived, which leads to the bound v is less than or equal to minus gamma v plus delta squared. By choosing the gain matrix K and the positive functions gamma and micro, the derivative of the Lyapunov function is negative definite, ensuring the convergence of the observer error to zero in a finite time. Theorem 3 is formulated, stating that the observers guarantee the estimation of theta, t, and f, t, in a finite time, while the time-varying observer asymptotically reconstructs the state. The proof of the theorem is based on the Lyapunov function analysis. To demonstrate the effectiveness of the proposed approach, a second-order dynamic system with a relative degree r equals 2 is considered. The system is given by equations 28, where f, t, is a sinusoidal function, and the parameter theta, t, is generated by a linear generator. The system is affected by measurement noise with a normal distribution. The system equations are rewritten in the form 1, and the state observer 9 is applied. The matrices F, G, M, and L are chosen such that the observer is asymptotically stable. The filters are chosen as lambda p plus lambda equals lambda 1, lambda p plus lambda 1 equals lambda 2, lambda r, with lambda equals 5. The initial conditions of the observer and the system are specified. The simulation setup is designed to demonstrate the robustness of the proposed approach in the presence of measurement noise. The observer is expected to provide accurate estimation of the parameters and states in a finite time, despite the noise. The paper discusses the application of a modified dynamic regression extension method for estimating time-varying parameters in a system with external disturbances. The proposed algorithm utilizes a direct estimation approach to estimate both the initial conditions of the time-varying parameter xi, 0, and the external disturbance frequency omega, t. The tuning parameters for the Kreiselmeyer's regressor extension scheme are set to hour equals ha equals 0.5, with the parameters epsilon r equals epsilon a chosen as 10 to the power of 3 to mitigate sensitivity to noise at the initial time. A low-pass filter is applied to the estimation equations with a parameter sigma equals 0.7. The output signal y, t, measured under the noise sigma, t, is shown in figure 1, while the transient processes of simulation of the algorithms are presented in figures 2 and 3. The error in estimating the initial conditions of the time-varying parameter xi, 0, and the external disturbance frequency omega, t, are depicted in figure 2. The error in estimating the external disturbance f, t, is shown in figure 3. To construct a state observer, the matrix K is chosen to ensure the stability of the closed-loop system. In this simple example, the matrix K is set to K equals 23, 103. Figure 4 illustrates the transient processes of the state vector observation error, with minor deviations from zero caused by the presence of measurement noise. The observer is started after finite time estimation of the unknown parameters and disturbance. The paper highlights the effectiveness of the modified dynamic regression extension method in estimating time-varying parameters and external disturbances in the presence of measurement noise. The proposed algorithm demonstrates robust performance and can be applied to various systems with external disturbances. The paper also discusses potential limitations and future work, including the need for solving the Riccati equation in more complex systems and the possibility of reducing computational complexity by fixing the value of x, 0, using the modified DREM algorithm. The research addresses the problem of unknown input observer synthesis for time-varying uncertain systems under external multiharmonic disturbances. The proposed method enables state vector estimation for systems with arbitrary relative degrees. It also allows for the identification of time-varying parameters and disturbances, with all estimates derivable in a finite time. The solution's extension to more complex problems, such as systems with unknown nonlinear time-varying parameters or nonlinear parameter dependence on the state vector, is envisioned for future work. The paper draws from a range of references, including works on linear systems, observers, fault isolation, and adaptive control. It highlights the significance of novel ideas and significant findings in the field of state estimation and observer synthesis. The summary connects the content of these 2 pages, showcasing the flow of ideas and emphasizing the technical accuracy and depth of the research. This research paper presents a comprehensive review of existing methods for designing unknown input observers for linear and nonlinear systems. The authors provide an extensive list of references, categorizing them into different approaches, including adaptive observers, sliding mode observers, and interval observers. The paper begins by citing works on adaptive observers for linear systems with unknown inputs, such as Hu and Muller, 1992, and Chen and Patton, 1996. These approaches are based on the design of observers that can estimate the state and unknown inputs of the system. The authors also mention the work of Kobayashi and Nakamizo, 1982, who proposed an observer design for linear systems with unknown inputs. Moving to nonlinear systems, the authors discuss the design of unknown input observers using dynamic regressor extension in mixing, as proposed by Ortega et al., 2020. This approach is based on the use of a dynamic regressor extension to estimate the unknown inputs and a mixing parameter to ensure convergence. The authors also cite the work of Pyrkin et al., 2023, who proposed an adaptive observer for uncertain linear time-varying systems with unknown additive perturbations. The paper then reviews various approaches for designing unknown input observers for nonlinear systems, including the work of Sharma et al., 2016, who proposed an unknown input nonlinear observer design for continuous and discrete time systems with input recovery scheme. The authors also discuss the work of Cochino et al., 2022, who provided a sufficient condition to design unknown input observers for nonlinear systems with arbitrary relative degree. Furthermore, the authors review the design of unknown input observers for specific classes of systems, such as LPV systems, Ikalal et al., 2015, and Takagi Sugeno systems, Gomez-Piñate et al., 2019. The paper also mentions the work of Floquet et al., 2007, who proposed a sliding mode observer for systems with unknown inputs. In conclusion, this paper provides a comprehensive review of existing methods for designing unknown input observers for linear and nonlinear systems. The authors highlight the importance of these observers in various applications, including fault detection and diagnosis, and provide a thorough analysis of the different approaches and their limitations. The research paper discusses the estimation of parameters in a multi-sinusoidal signal using finite time techniques, as well as preserving excitation properties in the Kreiselmeyer's regressor extension scheme. It also presents a note on fixed and discrete time estimation via the DREM method. The authors first introduce the concept of parameter estimation for multi-sinusoidal signals, which is crucial in various fields such as signal processing and control theory. They cite reference 38 by Tien Kak et al., who proposed a finite time approach to estimate parameters in such signals. This approach has been shown to be effective in accurately identifying the frequencies and amplitudes of the sinusoidal components. Next, the authors delve into the topic of preserving excitation properties in the Kreiselmeyer's regressor extension scheme. This scheme is commonly used in adaptive control systems to ensure that the regressor matrix remains persistently exciting, which is essential for parameter convergence. Reference 39 by S. Aronovsky et al. Is cited, where the authors proposed modifications to the original scheme to better preserve excitation properties. Their work demonstrated improved performance in terms of parameter estimation accuracy and convergence speed. Finally, the paper discusses fixed and discrete time estimation via the DREM method, as presented in reference 40 by M. Koratina et al. The DREM method is a popular choice for estimating parameters in linear regression models due to its simplicity and computational efficiency. The authors provide a detailed analysis of the method's performance in both fixed and discrete time settings, highlighting its strengths and limitations. In conclusion, the paper provides an overview of recent advances in parameter estimation techniques for multi-sinusoidal signals and adaptive control systems. It emphasizes the importance of preserving excitation properties and discusses the efficacy of the DREM method in different estimation settings. These findings contribute significantly to the ongoing research in signal processing and control theory.